Solar storms happen all the time. They rise, they fade, and most pass quietly through space. Planetary alignments happen too. Planets cluster, drift apart, and repeat the same slow dance over and over again. On their own, neither of these things is unusual. What's unusual is when they happen together during a moment when the solar system already seems more active than normal. Right now, a large cloud of solar material is moving toward Earth, large enough that scientists are watching it closely. At the same time, several of the solar system's largest players are occupying the same slice of space, clustered into a single sector rather than spread evenly along their orbits. December 31st, 2025. While most of the world was focused on calendars and countdowns, something quieter was unfolding on the surface of the Sun. A region known as Active Region 3914 released a solar flare, measured at M7.1. A solar flare is a sudden burst of energy, light and radiation released in a short flash. It moves at the speed of light, which means its effects reach Earth quickly. But the flare itself isn't what scientists were watching most closely. At nearly the same time, the Sun launched something heavier, a coronal mass ejection, or CME. If a flare is a flash, a CME is a cloud, a massive wave of solar plasma expanding outward into space, carrying its own magnetic field. That magnetic field is what matters. Because when a CME reaches Earth, it can collide with our planet's magnetic shield and trigger a geomagnetic storm, an event that can energize the upper atmosphere, intensify auroras, and place temporary stress on satellites, radio signals, and power systems. This is why, when people talk about a solar storm, they're usually talking about the CME, not the flare that came with it. In this case, tracking data suggested the CME was moving along a path that could intersect Earth. Based on current modeling, its estimated arrival window points to around January 3rd. Give or take several hours. These clouds don't travel through empty, uniform space, so their speed and timing can change as they move. None of this is unusual on its own. The Sun releases energy constantly. M-class flares happen. CMEs are a regular part of solar activity. What made scientists pay closer attention this time wasn't the category of the flare. It wasn't the strongest, and it wasn't rare. It was the combination. A flare and a CME released together from a region already under observation, moving into a solar system that appears more active than it was expected to be at this stage of the cycle. When people hear the phrase solar storm, they tend to imagine speed, a sudden udar, a fast-moving blast that hits Earth and moves on. But in space weather, speed alone is rarely the deciding factor. What matters more is how the pressure builds and how long it stays. A coronal mass ejection becomes disruptive not because it arrives quickly, but because of its physical profile. How dense it is, how structured it remains, and how persistently it presses against Earth's magnetic shield. Let's start with density. Some solar clouds are thin and diffuse. Others carry far more material than usual, packing a higher number of charged particles into the same volume of space. In this case, early estimates suggested densities approaching 50 particles per cubic centimeter. That's not extreme by historical standards, but it's high enough to increase how much energy can be transferred into Earth's magnetic environment. Then there's duration. A CME that sweeps past Earth quickly can sometimes do less overall work on the system than one that moves more slowly, maintaining steady pressure for many hours. It's a simple physical idea. A brief shove may knock something off balance. But sustained pressure is what gradually wears systems down. Speed still plays a role, of course. Current projections place this cloud's velocity in the range of 625 to 650 kilometers per second. Fast enough to be noticeable, but not unusually extreme. And that combination is exactly what makes this kind of storm easy to misunderstand. It isn't a record-breaking event racing toward Earth. It's a broad, structured cloud that continues to interact with the magnetosphere as it passes. This is also why solar images can be misleading. When scientists view a CME from the side, it can look thick and compact, like a dense wall moving outward. But when a CME is traveling more directly toward Earth, it may appear thinner on images, even though it actually spans a wider area of space. In other words, what looks subtle on a screen can still have a long-lasting physical presence once it arrives. So what does that mean in practical terms? Under current conditions, a G1 to G2 geomagnetic storm is considered a reasonable scenario. That's a low to moderate level on the geomagnetic scale. It's not a disaster category. It doesn't suggest widespread damage or dramatic global effects. But it is enough to produce stronger auroras at higher latitudes, and enough to place temporary stress on satellites, navigation systems, and power infrastructure, especially if the interaction lasts longer than expected. And this is the key idea. Lingering pressure beats sudden force. In space weather, the most influential storms are often the ones that keep pushing, not the ones that arrive with the most speed. But even this physical profile, density, duration, and velocity, still doesn't tell the full story. Because there's one more factor, invisible from images and difficult to predict, that ultimately decides how strongly Earth responds. And you usually don't know it until the very last moment. It's called magnetic field orientation, often referred to as BEES. Every coronal mass ejection carries its own magnetic field as it travels through space. When that field reaches Earth, its orientation determines how efficiently energy can pass into our planet's magnetic system. Here's the simplest way to understand it. If the magnetic field inside the CME points southward, it aligns well with Earth's magnetic field. Scientists call this strong coupling. Energy flows in more easily, the magnetosphere opens wider, and the storm becomes far more effective. If the field points northward, the interaction is weaker. The fields don't connect as cleanly, and much of the energy slips past without doing as much work. The difference can be dramatic. Two storms with the same speed, the same density, and the same duration can produce very different outcomes, all because of this one invisible orientation. A useful way to picture it is with magnets. When two magnets are aligned, they snap together. When they're misaligned, they resist. Earth's magnetic field behaves the same way. This is why space weather forecasts often change close to impact. It's not guesswork, it's physics. The magnetic orientation of a CME can't be measured accurately until the cloud is almost here. Satellites positioned between Earth and the Sun detect it only shortly before arrival, sometimes with less than an hour of clear warning. We won't know until the very last moment. That uncertainty isn't a weakness of science. It's simply the reality of how these systems work. And it leads to an important realization. The greatest risk doesn't come from the instant the CME arrives. It comes from how Earth's magnetic environment has been behaving before that moment. If the magnetosphere is calm and resilient, it can absorb more energy without much trouble. If it's already stretched, compressed, or unsettled, even a moderate storm can have a stronger effect. And once BZ turns southward, background conditions matter more than raw power. And that brings us to the next layer of the story. Long before the CME arrives, long before buzz is measured, something quieter can already be happening around Earth. Up to this point, everything we've talked about is still in motion. The CME hasn't arrived. The magnetic orientation hasn't been measured. Nothing dramatic has happened yet. And yet, the system may already be responding. This is the part of space weather that most people never hear about, because it unfolds quietly, long before there's anything to see. Scientists call it preconditioning. Preconditioning is what happens when Earth's magnetic environment is exposed to ongoing pressure before the main storm arrives. Not a single violent hit, but repeated lower-level interactions. Ahead of a large CME, the solar wind often becomes more unsettled. Smaller pulses of plasma move through space. The background flow becomes faster, denser, or more turbulent than usual. Individually, these changes don't look impressive. They don't trigger alerts. They don't produce headlines. But together, they begin to matter. Earth's magnetosphere, the magnetic bubble that shields the planet, responds to this pressure by slowly stretching and adjusting. On the day side, it compresses. On the night side, it elongates, forming a long magnetic tail. Over time, that constant push can change how the system behaves. Scientists sometimes describe this as magnetospheric softening. It doesn't mean the shield disappears. It means it becomes less resilient. A useful way to picture it is with a rubber band. If you stretch a rubber band briefly and let go, it snaps back easily. But if you keep it stretched for a long time, it loses some of its strength. The same thing can happen to Earth's magnetic defenses. Another analogy is a shock absorber. A well-rested shock absorber handles bumps smoothly, but one that's been under continuous load responds differently. It compresses more easily and recovers more slowly. When the magnetosphere has been under sustained pressure, its ability to absorb new energy can be reduced. This is why space weather scientists don't just watch the moment of impact. They monitor conditions days in advance. They track changes in solar wind speed and density. They watch how Earth's magnetic field responds to small fluctuations. They look for signs that the system is becoming more sensitive. Because when preconditioning is in place, the outcome of a storm can change. A CME that might normally pass with limited effects can produce stronger disturbances if it arrives after the system has already been stressed. And this leads to an important realization. You don't need a stronger storm to get a stronger response. You only need a system that's less prepared to absorb it. This is one of the reasons space weather can feel unpredictable from the outside. Two CMEs with similar speed and structure can produce very different results, depending on what happened before they arrived. From Earth's perspective, the difference isn't always visible. There may be no auroras yet, no disruptions, no obvious warning signs. Everything can look calm, even as the background conditions quietly shift. And when that happens, specific features of Earth's magnetic environment become far more important. If the shield has been stretched and softened, areas where it's naturally thinner begin to matter more. The system doesn't fail everywhere at once. It responds unevenly. Which is why scientists pay close attention not just to the storm itself, but to where the pressure is most likely to be felt. Because there is one particular region where this quiet weakening can have outsized effects. A place where Earth's magnetic protection is already less robust than average. And once the system is preconditioned, that weak spot becomes far more significant. That's the next piece of the story. A specific place on Earth where background conditions, quiet stress, and incoming energy all intersect. There is a specific place where this softening matters most. Up to now, we've been talking about conditions, about pressure building quietly, about a magnetic shield that can soften long before a storm arrives. But Earth's magnetic protection isn't uniform. It isn't equally strong everywhere. There is one region where the shield is naturally thinner, where charged particles reach closer to the planet than they do elsewhere. Scientists call it the South Atlantic Anomaly. The South Atlantic Anomaly, or SAAA, is a broad area stretching over parts of the South Atlantic Ocean and the eastern edge of South America. In this region, Earth's magnetic field is weaker than average. Not gone, but less intense. This isn't a sudden flaw, and it isn't new. The SAA exists because Earth's magnetic field isn't perfectly centered or perfectly symmetrical. The planet's molten iron core shifts and flows, and the magnetic field it generates is slightly tilted and offset from Earth's geometric center. As a result, the protective magnetic bubble dips closer to the surface in this one part of the world. Under normal conditions, that difference is manageable, but it has very real, practical consequences. Satellites passing through the South Atlantic Anomaly are exposed to higher levels of radiation than they experience elsewhere in orbit. Because of that, many spacecraft are programmed to temporarily shut down sensitive instruments while crossing the region. It's routine. Engineers expect it. They plan for it. Even so, the SAA is associated with higher rates of electronic glitches, memory bit flips, and radiation-related wear on satellite systems. It's one of the reasons space agencies monitor this region so closely. Now, here's where this connects directly to what we discussed earlier. Preconditioning doesn't weaken Earth's magnetic shield evenly. When the magnetosphere has been under sustained pressure, when it's been stretched and compressed over time, existing weak spots become more important. Think of it this way. If a shield is strong everywhere, pressure spreads out. But if part of that shield is already thinner, stress concentrates there. In that sense, a CME doesn't need to strike Earth head-on or affect the entire planet equally to matter. It only needs to interact strongly with the parts of the system that are least protected. This is why the South Atlantic Anomaly often comes up in space weather discussions. Not as a point of fear, but as a point of focus. When the magnetosphere is calm, the SAA behaves as expected. When the system has been preconditioned, its role can change. A CME arriving after days of sustained pressure may transfer energy more efficiently into this region. Particles that would normally be deflected higher up can penetrate deeper. Radiation effects can become more pronounced. Not everywhere, not all at once, but in specific places, at specific altitudes. This is an important distinction. The presence of a weak spot doesn't mean catastrophe. It means uneven response. And uneven response is often how complex systems behave under stress. This is why scientists don't frame the South Atlantic Anomaly as a danger zone for people on the ground. There's no immediate threat to daily life, no reason for alarm. The concern is technological, not personal. Satellites, navigation systems, communications infrastructure that relies on space-based platforms. These systems are designed with margins, redundancies, and safeguards. But they are also sensitive to conditions that push those margins repeatedly. And this brings us back to the larger theme of the story. The South Atlantic Anomaly didn't suddenly appear. It's been there for decades. What changes is the context in which it operates. When solar activity is low and Earth's magnetic environment is relaxed, the SAA is simply a known feature of the system. When activity increases and the magnetosphere has already been stressed, that same feature can take on greater significance. Not because it's new, but because the background conditions have shifted. This is why space weather can't be reduced to single events. A storm doesn't need to hit everywhere to matter. It doesn't need to be extreme to have consequences. Sometimes, it only needs to interact with the right part of the system at the right time. That's the idea that makes many people uncomfortable, because it challenges the assumption that risk is always obvious or evenly distributed. In reality, outcomes are shaped by structure, by asymmetry, by places where the system is already more vulnerable, and the South Atlantic anomaly is one of those places. But even this isn't the full picture. The magnetosphere doesn't just weaken quietly. It also shifts, responds, and reorganizes itself in ways that are harder to see. And to understand what happens next, we need to look beyond individual regions and start thinking about how larger patterns emerge. Because what we've been describing so far, preconditioning, weak spots, uneven response, is only one layer of a much bigger system. And this brings us to the part of the story that makes many people uncomfortable. Before we go any further, we need to be very clear about one thing. This is not astrology. It's not a perfect straight line. And it's not about hidden forces or mystical influence. What we're talking about here is something far simpler and far more grounded in physics. It's a planetary configuration. At certain moments, several planets occupy the same general region of the solar system, not stacked neatly in a line, but clustered within a relatively narrow slice of space. In this case, that slice is roughly 60 degrees wide. Within that sector, you'll find Jupiter, Earth, Mercury, Venus, and Mars, all residing in the same broad neighborhood, rather than being evenly distributed around the Sun. This kind of clustering isn't common, but it isn't unprecedented either. It happens from time to time as planets move along their orbits at different speeds. What matters isn't the geometry itself, it's the timing. Right now, Earth is approaching perihelion, its closest point to the Sun, an event that occurs in early January every year. At nearly the same time, Jupiter is nearing opposition. When Earth passes between Jupiter and the Sun, placing the giant planet relatively close in cosmic terms. Individually, none of this is unusual. But together, it creates a moment where several of the solar system's largest players are dynamically aligned in time, not space. From a traditional textbook perspective, the effect of planetary gravity on the Sun is extremely small. That's the scientific consensus. The Sun outweighs all the planets combined by an enormous margin. No alignment of planets is going to pull a solar flare into existence or cause a CME by brute force. That part is clear. And yet, there's a subtle question scientists continue to explore. What happens when a system is already near a threshold? In complex systems, outcomes aren't always determined by large forces alone. They're shaped by background conditions, by how close the system is to changing state. Think of it like a balance. When the balance is far from tipping, small influences don't matter. But when it's already close, timing and coordination can make a difference. This doesn't mean planets are triggering storms. It means they may slightly shift how energy moves through a system that's already active. In this context, planetary clustering isn't a cause. It's part of the environment, a background condition. And that's why scientists pay attention to it, not as a prediction tool, but as a piece of context. Because over time, patterns begin to emerge. Periods of heightened solar activity have a tendency to coincide with moments when multiple background factors overlap. Strong solar cycles, unusual configurations, and systems operating closer to their natural limits. That doesn't establish cause and effect, but it does invite careful observation, especially when the system in question, the Sun, is anything but simple. This is where the idea of complex systems becomes useful. In complex systems, responses aren't always linear. Small inputs don't always produce small outputs, and effects don't always appear immediately. Sometimes they emerge after delays. Sometimes they depend more on when something happens than on how strong it is. This is why timing matters more than force in many natural systems. And it's why the current configuration deserves attention without alarm. Not because it guarantees anything, but because it adds another layer to the background conditions we've been discussing. Context changes how systems respond. That's the key idea here. The Sun doesn't operate in isolation. Neither does Earth's magnetic environment. They're embedded in a larger, dynamic system where multiple factors overlap, interact, and sometimes reinforce one another. And when those factors line up in time, even loosely, it can change how the system behaves. That brings us to the next concept. If small influences can matter under the right conditions, then we need a way to describe how those influences build, combine, and take effect. To understand how something small might matter, we need to talk about resonance. To make sense of everything we've discussed so far, we need to talk about one idea that shows up across physics, engineering, and nature itself. It's called resonance. Resonance doesn't require a large force. It requires timing. When a small force is applied again and again, at just the right moment, its effects can add up. Not all at once, not immediately, but steadily. A simple example is a playground swing. You don't need a strong push to make a swing go higher. You just need to push it at the right time, over and over again. Each push adds a little more energy until the motion becomes obvious. Another example is a bridge. If people walk across it randomly, nothing happens. But if footsteps line up with the bridge's natural rhythm, the structure can begin to sway. The force hasn't increased. The timing has. That's resonance. Now, resonance doesn't mean something will fail. It means the system becomes more responsive to inputs that match its natural behavior. And that brings us back to the solar system. We often imagine the Sun sitting perfectly still at the center, with planets circling around it like clockwork. In reality, the picture is more subtle. The Sun and its planets orbit a shared point known as the barycenter, the center of mass of the entire system. Because planets like Jupiter carry so much mass, that shared center can lie just outside the Sun itself. As a result, the Sun doesn't stay perfectly fixed. It moves slightly, tracing a slow, complex path as the planets shift. These motions are small, extremely small compared to the Sun's size and energy. On their own, they don't cause solar activity, but they do introduce gentle, repeating patterns, background rhythms that interact with an already active system. And here's the crucial point. In complex systems, effects don't always appear immediately. There can be delays. Energy can build quietly. Responses can emerge only after certain thresholds are crossed. This is why scientists are careful about drawing straight lines between cause and effect. Something may happen today, and its influence may not show up until days or even weeks later, after it's interacted with other conditions, other pressures, other rhythms. That idea becomes especially important when a system is already operating near its limits. Which brings us to the present moment. Solar cycle 25 has turned out to be more active than many early predictions suggested. Sunspot numbers have risen faster. Eruptions have been more frequent. In other words, the baseline level of activity is higher than expected. When a system's baseline rises, its sensitivity changes. Small disturbances that would normally fade into the background can begin to matter more. This doesn't mean planetary configurations are driving solar storms. It means they may slightly modulate how energy moves through a system that's already energized. Alignment isn't the cause. It's part of the timing. And timing matters most when a system is close to a transition. This is what scientists refer to as criticality. Near a critical point, systems behave differently. They become more responsive, more variable, more likely to produce noticeable effects from relatively modest inputs. That's why identical events can have different outcomes at different times. It's not the event that changes. It's the state of the system receiving it. Seen this way, the current moment isn't remarkable because of any single factor. Not the CME, not the alignment, not the solar cycle on its own. It's the overlap, higher background activity, ongoing magnetic pressure, structural weak spots, and timing that brings multiple influences together. None of these guarantee anything dramatic, but together, they help explain why familiar events can feel different, why patterns appear to shift, and why scientists pay attention even when nothing immediately happens. Because in complex systems, waiting for a single dramatic trigger often means missing the real story. The real story is how conditions evolve, and once a system crosses a certain threshold, its behavior changes. Sometimes subtly, sometimes suddenly, but rarely without warning. And once a system crosses a certain threshold, patterns begin to change. So far, we've been looking outward, at the sun, at space weather, at systems under increasing strain. Now, we turn our attention back to Earth. Not to make dramatic claims, not to draw simple lines of cause and effect, but to notice something quieter. At the same time, solar activity has been elevated, and as a CME has been moving through space toward Earth, our planet has been doing what it always does, releasing stress. In late December, a magnitude 6 class earthquake occurred off the coast of Japan. Not unprecedented, not unexpected for that region. Japan sits along one of the most active tectonic boundaries on the planet. Earthquakes of this size happen there regularly, and this point matters. There's no scientific basis for saying a solar flare causes an earthquake. That claim goes beyond evidence, and we should be clear about that. What we can talk about is timing and context. Earthquakes don't happen in isolation. They occur when tectonic stress has been building for years or decades along fault lines already near their limits. When enough stress accumulates, release becomes inevitable. To understand how sensitive these systems are, it helps to remember how earthquake energy works. The magnitude scale isn't linear. Each increase by 1 full magnitude represents roughly 32 times more energy released. A magnitude 6 event isn't just slightly stronger than a magnitude 5. It's dramatically more energetic. But it's also well within the normal range for a highly stressed tectonic zone like Japan's. So what's the relevance here? It's not that something caused the quake. It's that multiple systems appear to be operating under elevated baseline stress at the same time. The sun is more active than expected for this point in its cycle. Earth's magnetic environment has been under sustained pressure, and Earth's crust constantly shifting, continues to release accumulated energy where it's weakest. These are independent systems. They obey different physical laws. They operate on different timescales. But they share something important. They all respond differently when they're already close to their limits. In geology, engineers often describe this idea using a familiar phrase: the straw that breaks the camel's back. The straw doesn't supply most of the force. It simply arrives at the wrong time. That doesn't mean small disturbances cause large events. It means systems under high stress can respond abruptly to minor changes. This is why scientists are careful with language. They use words like observed, correlated, and monitored. They avoid declaring causation where none has been proven. At the same time, they don't ignore patterns. When multiple systems show signs of strain simultaneously, it invites broader observation, not alarm, not speculation, just attention. Earth's interior has its own rhythms, its own cycles of stress accumulation and release. Those processes are driven by plate motion, mantle convection, and internal heat, not by solar activity. But the timing of when stress releases can cluster naturally during periods when background conditions are already elevated. That clustering doesn't require a single external trigger. It emerges from systems that are already carrying heavy loads. This is why moments like this can feel unusual, even when nothing extraordinary is happening in isolation. A CME on its way, an earthquake in a known seismic zone, subtle shifts in Earth's magnetic environment. Individually, none of these are shocking. Together, they create a sense of pressure, of multiple layers of activity unfolding at once. And that's the point. Correlation is not causation, but context still matters. Context shapes how we interpret events. It shapes how scientists decide what to watch more closely. And it shapes how systems respond when additional stress arrives. Earth doesn't react because of a headline. It reacts because of physics. And physics tells us that systems under long-term strain don't need dramatic triggers to change behavior. They only need time. This doesn't mean we're heading towards something catastrophic. It means we're observing a period where baseline stress appears elevated across multiple domains. That observation alone is enough to justify careful monitoring. And it raises a larger question. If this sense of pressure feels more frequent, if events seem to cluster more often than they used to, then perhaps the explanation doesn't lie in any single storm, quake, or configuration. Perhaps it lies in something broader. Something about how cycles overlap, how baselines shift, and how systems behave when long-term conditions change. To understand why this pressure feels more frequent, we need to zoom out even further. To understand what all of this really means, we need to step back. Not to a single storm, not to a single alignment, but to the rhythm that governs all of it. The sun follows a cycle. Roughly every 11 years, solar activity rises and falls. Sunspots increase, magnetic fields tangle, eruptions become more frequent. And then, gradually, things quiet down again. This pattern is known as the solar cycle. For decades, scientists have used it as a reference frame. It helps define what's typical, what's unusual, and what counts as extreme. And when solar cycle 25 began, many early models suggested it would be relatively weak. Lower sunspot numbers, fewer intense eruptions, a calmer period overall. That was the expectation. But the sun didn't follow the script. As real data began to arrive, a different picture emerged. Sunspot counts climbed faster than predicted. Active regions became more complex. Strong flares appeared earlier and more often than models had anticipated. In short, Solar cycle 25 turned out to be stronger than expected. This matters for a simple reason. We judge events relative to a baseline. The baseline is the background level of activity we consider normal. It's the reference that tells us whether something stands out or blends in. If the baseline is low, moderate events look dramatic. If the baseline rises, the same events can start to feel routine. And here's the key question. What happens if the baseline itself has shifted? Imagine heating a pot of water. When the water is cool, small bubbles mean something is changing. As the temperature rises, bubbles become more common. Near boiling, they appear constantly. The bubbles didn't suddenly become more powerful. The system moved closer to a threshold. Solar activity behaves in a similar way. As the baseline level of magnetic complexity increases, events that once seemed rare can occur more often. Not because each event is stronger, but because the system is operating in a more energized state. This is where the idea of criticality becomes important again. Systems near a critical point don't respond in smooth, predictable ways. They become more variable, more sensitive, more prone to producing clusters of activity. That doesn't mean disaster is inevitable. It means variability increases. Which brings us back to something we've seen repeatedly throughout this story. The storm will pass. The CME will move on. Auroras will fade. But the conditions that made those events possible may remain. This is why focusing only on individual events can be misleading. If we treat each flare or storm as an isolated incident, we miss the broader trend. What's changing isn't necessarily the size of the events. It's the environment in which they occur. Events don't change, baselines do. And when baselines shift, our old expectations stop working. What once felt exceptional begins to feel frequent. What once demanded explanation starts to feel normal. That doesn't mean the system is broken. It means it's evolving. This perspective also explains why so many of the moments we've discussed feel connected, even when they aren't directly linked. Higher solar activity, sustained pressure on Earth's magnetic environment, weak spots that matter more under stress, multiple systems responding during the same general window of time. These aren't signs of a single cause, they're signs of overlapping cycles. And understanding overlapping cycles requires patience. It requires resisting the urge to label every event as a warning or an anomaly. It requires stepping back and asking whether the frame of reference itself needs to change. Because if we're still measuring today's activity with yesterday's baseline, we're going to misinterpret what we see. This is also why modern space science looks different than it did a few decades ago. We're no longer limited to isolated observations. We now track patterns across years, across cycles, across entire systems. We look for gradual shifts rather than sudden surprises, for changes in background behavior rather than singular triggers. That approach doesn't always produce dramatic headlines, but it produces something more valuable. Understanding. Understanding that complex systems don't announce transitions with alarms. They drift, they accumulate, they change character slowly, and then all at once. Solar cycle 25 isn't remarkable because it's unprecedented. It's remarkable because it reminds us how much context matters. The sun isn't doing something strange. It's doing what dynamic systems do when conditions evolve, and Earth, embedded within that system, responds in its own way. This is the big picture. Not a prediction, not a warning, but a shift in perspective. Once we see that the baseline itself may be changing, everything else begins to make more sense. And this is where the story turns again. Because while we're still learning how these shifts unfold, We've also developed new ways to notice them. Tools that can detect subtle changes long before we fully understand what they mean. And this is where modern data tools quietly enter the picture. Modern space science doesn't suffer from a lack of data. It suffers from too much of it. Every day, telescopes and satellites record vast streams of information. Solar images taken every few seconds, magnetic field measurements sampled continuously, particle counts, radiation levels, plasma flows. No human team could possibly watch it all in real time. Even the most experienced scientists have limits. You can't stare at thousands of data channels at once. You can't notice every small deviation as it happens. That's where automated systems quietly come in. These systems aren't designed to predict the future. They don't understand physics in the way humans do. They don't know what a solar storm means. What they do know is pattern. Over time, they learn what normal looks like, how signals usually behave, how measurements typically rise, fall, and fluctuate. And when something doesn't match that learned baseline, they flag it. Not as danger, not as explanation, just as difference. Think of it like a weather radar. The radar doesn't know whether a storm will flood a town. It simply notices when rainfall intensity or structure looks unusual. Or consider credit card fraud detection. The system doesn't understand why a purchase was made. It only recognizes when spending patterns don't look like they used to. Space science uses the same idea. Automated systems scan incoming data and ask a simple question. Does this look like before? If the answer is no, the data gets marked for closer inspection. And this is an important point. These systems don't need to understand causes. They don't interpret meaning. They don't draw conclusions. They operate purely at the statistical level. AI doesn't need to understand. It needs to notice. That makes it useful in a very specific way. It can highlight subtle changes in shape, timing, or progression, details that are easy to miss when looking for dramatic spikes or obvious events. In the context of solar activity, that means noticing things like patterns unfolding more quickly than expected, structures that linger longer than usual, or sequences that don't quite match historical examples. None of this proves anything on its own. A flagged anomaly isn't a prediction. It isn't a warning. It's simply a signal that something looks slightly different from the established norm. And in a story that's been about shifting baselines, that matters. Because when conditions evolve gradually, the earliest signs often aren't dramatic. They're statistical, quiet, incremental, easy to dismiss unless you're looking at the full data set. This is why scientists increasingly rely on automated tools. Not to replace judgment, but to extend perception. To notice what no single observer could catch alone. And in this case, these systems didn't flag something because it was especially powerful. They flagged it because of how it unfolded, the structure, the progression, the way it compared to similar events in the past. That's the detail we need to look at next. Because among all the data streams and background patterns, one particular feature stood out, not as extreme, but as unusual. And what these systems flagged was something subtle, but important. Among all the numbers, charts, and timelines, one detail stood out. Not because it was dramatic, not because it broke records, but because it didn't behave the way similar situations usually do. The active region on the Sun had a familiar configuration. Magnetic fields tightly wound, energy clearly stored. In many past cases, regions like this go on to produce stronger flares, sometimes rapidly, sometimes in sequence, but usually with a sense of release. This time felt different. Instead of a full discharge, what we saw looked more like a partial release. Some energy was let go, enough to produce a noticeable flare and an accompanying CME, but not enough to fully relax the magnetic structure that created it. A useful way to picture this is with a compressed spring. If you compress a spring and let it go completely, it snaps back and settles. The stored energy is released and the system relaxes. But if the spring only partially releases, some tension remains. The system hasn't reset. It's changed state, but it hasn't returned to equilibrium. That's what made this storm interesting to scientists watching closely. The magnetic complexity of the region didn't collapse the way it often does after a major release. Instead, parts of it remained intact, still twisted, still energized. This doesn't mean something bigger must follow. And it's important to say that clearly. Solar physics doesn't work on guarantees. Plenty of active regions release energy in stages and then quiet down. Sometimes a partial release is simply the end of the story. But sometimes it isn't. This is why researchers use careful language. They don't say something will happen. They say this is worth watching. Because in systems that are already operating near their limits, partial releases can matter. If the broader environment is calm, residual energy often dissipates harmlessly. If the environment is stressed, if the baseline is elevated, that remaining tension can interact with what comes next. And that brings us back to the central theme of this entire story: conditions over events. The unusual aspect here wasn't the size of the flare. It wasn't the speed of the CME. It wasn't any single metric. It was the pattern. The way energy appeared to be released incompletely. The way the system settled into a new configuration rather than fully relaxing. The way this happened against a background of heightened activity. Seen in isolation, none of this is alarming. Seen in context, it becomes interesting, especially when paired with everything else we've discussed. A magnetosphere already under sustained pressure. Weak spots that matter more when the shield is tired. A solar cycle operating above early expectations. Subtle statistical signals flagged by automated systems. Individually, these are just observations. Together, they form a pattern, not of danger, but of sensitivity. And sensitivity changes how systems respond. This is where the mystery deepens. Because the most intriguing part of this storm may not be what happened, but what didn't. There was no dramatic cascade, no runaway escalation, no clear endpoint. Instead, there was a pause, a sense that the system had shifted, but not finished adjusting. For scientists, moments like this are uncomfortable in a very specific way. They don't fit neatly into models. They don't offer clean conclusions. They resist simple storytelling. But they are often where the most important insights begin. Because nature doesn't always move in clean chapters. It evolves through overlaps, delays, and partial transitions. And when energy isn't fully released, it doesn't disappear. It remains part of the system, redistributed, reconfigured, waiting to interact with future conditions. Again, this is not a prediction. There is no countdown, no implied outcome. Only a recognition that the story may not be complete. And that recognition matters precisely because it keeps us from rushing to conclusions. In science, uncertainty isn't a weakness. It's a signal to pay closer attention. That's why this detail, the partial release, has drawn so much quiet focus, not because it promises something dramatic, but because it suggests the system is still adjusting, still responding, still carrying memory of what came before. And that idea, that systems remember stress, that they don't always reset cleanly, has appeared again and again throughout this story. From Earth's magnetosphere to tectonic plates to the sun itself. This storm wasn't remarkable for how much energy it released. It was remarkable for how much it didn't. And when multiple systems are operating near their limits, those kinds of gaps, those unfinished releases, are often where the next questions begin. Because in complex systems, the end of one event isn't always the end of the story. Sometimes it's just a transition. And this wasn't the only signal showing up at the same time. In science, a single anomaly rarely means much on its own. An unexpected data point can be noise. A one-off event can be coincidence. Even something unusual can turn out to be perfectly ordinary once you see more context. That's why scientists are trained to be cautious. They don't react strongly to isolated signals. They wait. But there's a moment when waiting turns into listening. That moment comes when multiple small anomalies begin to appear close together in time, especially when they show up across different systems. This is what researchers often refer to as stacking. Not stacking in the sense of piling evidence to prove a claim, but stacking in time. Overlapping signals that wouldn't matter much alone, yet start to feel different when they arrive together. The key idea is simple. One anomaly can be ignored. Two might raise an eyebrow. Several, arriving within the same window, invite closer attention. Not panic, not conclusions, just attention. We've already seen parts of this picture. Solar activity during solar cycle 25 has been higher than early models predicted. That's not alarming. But it is a shift in baseline. Earth's magnetic environment has shown signs of sustained pressure, responding to ongoing solar wind conditions rather than a single impact. A major active region released energy only partially, leaving behind magnetic complexity instead of fully relaxing. Each of these observations is modest. None of them demand dramatic interpretation, but they don't exist in isolation. At the same time, astronomers have noted something else. The rate at which near-Earth objects are being detected has increased, not because space suddenly became more crowded, but because detection systems have improved. Better surveys, wider coverage, more sensitive instruments. Most of these objects pose no threat. They pass quietly, cataloged and forgotten. Still, the increase matters, not as danger, but as data. More detection changes our sense of what's common. It reshapes our expectations of background activity. Meanwhile, in stellar observations beyond our solar system, astronomers have recorded occasional outbursts from stars that are usually quiet. Again, nothing extreme, nothing unprecedented, but interesting in timing. And then there's a different kind of witness moving through all of this. An interstellar visitor, 3 Atlas, passing through the solar system, not as a cause, but as an observer. It's not interacting with Earth. It's not influencing the sun. And it isn't responsible for any of the activity we've discussed. But it is moving through a solar environment that's anything but calm. As it travels, it experiences variations in solar wind, magnetic fields, and plasma density. Conditions shaped by the same background activity affecting everything else. Some observations of its motion and brightness have been difficult to model precisely. Not alarming, just complicated. And that's the point. None of these signals are being treated as causes. No one is drawing a straight line from one to another. What scientists are noticing is overlap. Multiple systems, different scales, independent processes, all showing signs of elevated activity within the same general window of time. This is where the orchestra analogy becomes useful. When an orchestra warms up, you don't hear a single sound. You hear fragments, a violin tuning, a horn testing a note, percussion tapping softly. None of it is music yet. None of it is alarming. But together, it tells you something important. The system is active. Energy is moving. Something is about to take shape. Stacking anomalies that feel like that. Not an explosion, not a climax, a convergence. And this is why scientists resist dramatic interpretations. They know that complex systems don't announce transitions with clear signals. They shift gradually. They overlap. They change character before they change behavior. This perspective also helps explain why moments like this feel unsettling to the public. We're used to thinking in terms of single causes and single effects. One storm, one trigger, one explanation. But reality is rarely that tidy. When baselines shift, when systems approach sensitivity, when multiple cycles overlap, events start to cluster. Not because something is wrong, but because conditions allow it. That doesn't mean something catastrophic is coming. It means context matters more than ever. It means old assumptions about rarity may need updating. It means patterns deserve attention even when outcomes are uncertain. This is why researchers emphasize observation over prediction. They don't ask, what will happen next? They ask, what is the system telling us right now? And right now, the message isn't danger, it's complexity. A reminder that the solar system is dynamic, that Earth is embedded in overlapping cycles, that stress, timing, and background conditions shape outcomes in subtle ways. Stacking signals don't demand fear. They demand humility. They remind us that understanding comes from patience, from holding multiple ideas at once, from resisting the urge to simplify too quickly. So the question isn't whether something catastrophic is coming. The question is how we respond when patterns begin to change. The CME is on its way. It will reach Earth. It will likely create some auroras. It could cause temporary stress on satellite systems, power grids, and communications networks. But in the grand scheme of things, this is a short-term event. The storm will pass. It will dissipate, and things will settle back to normal. In contrast, what really matters are the conditions, not just the event. The event is fleeting, an energetic burst that comes and goes. The conditions, however, are longer lasting. They shape how the system responds, not just to one flare, but to everything that comes next. We tend to think of the universe as stable. We think the stars and planets are fixed in place, that they operate on eternal rhythms, like clockwork. In truth, the universe is a dynamic system, one in constant motion and change. Everything is in flux. Nothing is truly still, and that includes us. The sun is not a constant, unmoving force. It is an active, ever-changing body, constantly shifting and evolving. And Earth is not just a passive observer. We live in a universe where we cannot control the sun, the solar winds, or the cycles of activity that come with them. But there are things we can control. We can control our attention, where we focus our thoughts, where we place our awareness. We can control our breathing, the way we respond to stress, to the unknown. We can control our reaction to the cosmic forces at play, even if we can't control the forces themselves. And so, tonight, let's remember, you don't need to act. You don't need to respond right away. You don't need to change anything right now. The sun is far away. The CME is still on its way to us, moving slowly across the vast emptiness of space. But here, on Earth, it's quiet. And right now, in this moment, You are safe. Earth is still spinning on its axis. Our magnetic shield is still holding steady, protecting us from the sun's energy. The universe, vast and incomprehensible, continues its dance. But it is not out to get us. It is simply moving, as it always has. The most important thing to remember is this: nothing needs to be done right now. You don't need to prepare. You don't need to worry. You just need to be. Tonight, you're allowed to rest. There is no rush. There is no danger. Just the quiet hum of the universe as it continues its eternal journey. The universe keeps moving. And tonight, you're allowed to rest.